Hey everyone. Okay, so lesson 12, video 12, we're going to dive into probability. Now, essentially, probability, you guys have been doing probability for a long time, okay? The concept of probability is first introduced to you like way in elementary. And that overall concept is what I really just need you to keep in mind the whole way through. That overall concept is probability is the favorable outcomes over the total outcomes, okay? So we always take what's favorable over what's totally possible. And then that gives us our probability. Now, probability can be written as a fraction, or we could write it as a decimal, or we could change that decimal into a percentage, okay? So you just need to make sure you're reading the question and answering in whatever format the question is asking you to do, okay? All right, so I got to go through a bunch of vocabulary with you, and then we'll try some examples. To the right there, that, again, yellowish, greenish, I don't really know what color that is, but whatever color that is, those are the things that are on your formula sheet. Now, right away, what I want you to do is maybe make some notes on your sheet just to say what each of these are, okay? These guys are mutually exclusive, and I'll talk about what each of that means in a second, but this is not mutually exclusive, okay? And then these are dependent events. At the very bottom, I skipped the other guy for a second, and then these are independent. I partly skipped because I was trying to figure out how I was going to represent the letters of independent, but that'll do. Okay, so we got mutually exclusive, not mutually exclusive, and then independent events and dependent events. And I'll talk about each one of those as we go. Okay, so an event refers to a possible outcome of an experiment. Probability is the confidence that an event will happen. It is calculated by the amount of favorable outcomes divided by the amount of total outcomes, which is what I wrote on the board back there, okay? Theoretical probability is what you should get, and experimental probability is what you actually get when you run an experiment. They're often not the same because probability involves chance, right? If I flip a coin, if I flip a coin 10 times, there is a possibility that I would get 10 heads right in a row, okay? It's a very unlikely possibility, but it is a possibility. And so that's an example where my experimental probability would not match my theoretical probability. If I flipped a coin 10 million times, then they'll match, okay? So the experimental probability and the theoretical probability match up with a massive amount of trials, but with a little bit of trials, they won't always match, okay? Okay, odds represent, now odds are new to grade 12. Odds represent the likelihood of something occurring. Odds can be expressed in favor or against. Either way, what you're looking for is what gets stated first, okay? The leftover bits get stated at the end. Odds are written as part over part, whereas probability is written as part over whole. And that's the big difference between odds and probability that you got to be careful with, because they will ask you to convert between the two, okay? I often get kids at school to think about the fat strategy, okay? So write the word fat on your question, and then you're gonna write the number that's for, the number that's against, and then the total. That way, you have it all being thought of. So right away, if they say the odds of something are 3 to 5, 4 is 3, 5 is against, but now you can see the total has to be 8. So if they ask what's the probability of something happening, then it would be 3 over 8 instead of 3 to 5, okay? Okay, complementary events add up to 100. They're essentially, the combination of complementary events essentially is everything that could happen. So either it could rain or it could not rain. Those are complementary events. The probability of it raining or not raining is 100%, right? Because those are the only two options I have. Either it's going to rain or not rain, okay? Winning the lottery is complement to not winning the lottery. You have 100% probability that one of those is going to happen, okay? All right, when you are looking at the probability of different events at the same time, you multiply the probabilities together. So look for and in the question. What is the probability of what is the probability of event A and event B happening? So then you would multiply the probability of A and the probability of B together. Independent events are those where the outcome of one does not affect the other. Watch for the phrase with replacement. So it's like I draw a card, I put it back in the deck, and I draw a card again. Or I grab a marble, I put it back in the bag, and I draw a marble again. Those would be independent events. The outcome of the second event has no bearing on the first event. If the outcome of the first event does affect the outcome of the second, then those are dependent. And what happens is, essentially, my population will change, right? So if I had a bag of 25 marbles, and I'm going to draw the first marble, and I'm not going to put it back, the probability for the second marble now changes because I'm one marble less. Okay, and so remember when I outlined all of this, this would be the dependent event. That expression there just means the probability of B given A. So it's the probability of the second event given that the first event has already happened. Okay. Okay, when grouping multiple events together, we're adding the separate probabilities. So you're going to look for or there. If it's the probability of event A or event B happening, then you would add those two probabilities together. So when it's an and, you're multiplying and you're trying to think of whether these are dependent or independent events. When it's an or, you're adding and you're trying to think of whether they're mutually exclusive or not mutually exclusive. Now, these words cause headaches among 30-2 students. And it's partly because we always assume it's the other way. So I want to be very careful here for a second, and I want to think about the word exclusive. If you are excluding somebody, you're not letting them into your group, right? You're keeping them separate from you. So when we say mutually exclusive, what we're saying is these two things have no overlapping region, okay? They want nothing to do with each other. One's over here, and there's no overlap, okay? So mutually exclusive events have nothing to do with each other. They have no common ground, no overlap. Think about a Venn diagram, okay? There's just a circle here, a circle here. When they're mutually exclusive, you have that top guy up here, and you just add those separate probabilities together. When there's an intersection, we say that they're not mutually exclusive, and that's where it gets confusing, because when there is an intersection, we say not mutually exclusive. So you got to be really careful with that. When you add these events together, you have to subtract the overlap. Otherwise, you counted it twice. Okay, so what happens is if I had the probability of A and the probability of B, okay? And let's just say I had, I don't know, 10, 20, 30. Well, the probability of A is 30, right? Because the whole circle is A. So the probability of A is 30, and the probability of B is 50. Okay, but that's not the probability of A or B. 30 plus 50 is 80. If I added the probability of A or B, I should only be getting 10 plus 20 plus 30, that I should only be getting 60. Okay, and what happened is because I added this circle and this circle together, I actually added that overlap 2 times. So what I have to do is I have to add the probability of A with the probability of B, but then I have to take away an intersection. And the reason I'm taking away an intersection is because I've counted that intersection twice, okay? And that's where this formula here is coming from, okay? This is the probability of not mutually exclusive events, and I'm subtracting that overlap. Okay. All right, so let's try some questions together. A contestant in a game must draw a single cube from a bag containing 7 red cubes, 4 blue cubes, and 2 white cubes. The odds in favor of the contestant drawing a white cube. Well, it's odds, so that's in favor to against. Okay, so I have 2 white cubes and I have 11 non-white cubes. So it'd be 2 to 11. Okay. The names of 25 students, including Adam and Erica, are entered into a draw for 2 different prizes. Names will be randomly drawn without replacement. Okay, there's a key word there, without replacement, to determine the winners. Which of the following expressions can be used to determine the probability that Adam and Erica will win both prizes? Okay, so to get the first prize, how many events are favorable and how many are total? Well, I have 2 events favorable. Either Adam could get it or Erica could get it. Okay, out of how many are in total? 25 are in total. So for the first probability, I'm going to have 2 over 25 because I've got Adam and Erica here and I've got 25 prizes. For the second probability, remember, because they're dependent events, the second probability assumes the first probability has occurred. Okay, so if one of those people have already gotten a prize, then they're not both available to get the prize anymore. So now there's only one favorable outcome, whoever didn't get the prize. And one of the draws has already happened, so there's not 25 students. Sorry, I think earlier I said 25 prizes. It was 25 students. That'd be good if everybody got a prize. Just like your old soccer teams where everybody got a trophy. I digress, sorry. So there's no longer 25 students in the draw because one prize has already been drawn. So now there's 24 students in the draw. Okay, so see how it changes the population when it's independent. So that's going to be C. Okay. Okay, the probability of randomly selecting a person with brown eyes is 0.48. The probability of randomly selecting a person with blue eyes is 0.17. The probability of selecting a person that doesn't have brown eyes or blue eyes. Well, either I have brown eyes, or I have blue eyes, or I don't have brown eyes or blue eyes. Okay? Doesn't matter all the other shades you're thinking about. Those 3 items are complementary events because either I have brown eyes, or I have blue eyes, or I don't have brown eyes or blue eyes. Okay? So they all have to add up to 100. So I just go 1 minus 0.48 minus 0.17. The probability of having neither brown eyes nor blue eyes would have to be 0.35. Okay, just a little reminder, I know you guys know this, but when putting these into numeric response, a decimal has to start with 0, not the decimal place, and the decimal place gets its own number. Okay, so you would have to key this in as 0.35. Okay, a newspaper article claimed that a new medication doubled the probability of successful treatment compared to an older medication. The odds of the older medication being successful in the treatment were 3 to 7. According to the new authors, the odds in favor of the new medication being successful. Okay, well, let's think about this fact scenario here for a sec. I've got the odds in favor are 3 to 7. Okay. Now, that means the total is 10, which means the probability that the first guy works is 3 out of 10. Okay. Remember, it didn't say it was doubling the odds. It said it was doubling the probability. So if I'm going to double the probability, well, 3 over 10 doubled is 6 over 10. Okay. So if I times that by 2, I'll get 6 over 10. Now 6 over 10 reduces to 3 over 5. Okay. Everybody good? Now, think that through. I need to put that back into my fat scenario. So odds for are 3, and the total, remember, because that's probability, the total is 5, which means odds against have to be 2, because it has to go 3 plus 2 equals 5, okay? And so it'll be 3 to 2 now instead of 3 to 7. Okay, so the answer has to be D there. Okay, a survey of Alberta students was used to estimate the percentage of students who participate in school and non-school athletics, as well as percentages who do not participate in any athletics. The results of the survey are shown in the Venn diagram. The odds in favor of randomly selecting an Alberta student who participates in school athletics. So odds in favor, what I want is participation, and what I don't want is non-participation. So participation would be these guys, because we're doing school athletics, and then non-participation would be those guys, okay? So 15 plus 38 is 53, and 26 plus 21 would be 47. So the answer is 53 to 47. Okay. Okay. The odds in favor of the spinner landing on the region labeled red on the spinner shown below are 1 to 4. Okay, so if I look at that, I've got 1 favorable, 1, 2, 3, 4 against. A new spinner is being developed. The red region will be twice as large, and the green region will be eliminated. So essentially, I'm just going to hide myself for a second so you can see this. This is now going to be red along with this. Okay, so now I'm looking at the odds in favor of the spinner landing on the red in the new guy. Okay, let me just put myself back. So it'll be 2. There are 2 sections now that are favorable and 3 sections that are not favorable. Okay, so it ends up being 2 to 3. Okay, the odds in favor of Macy passing her driver's test on the first try are 7 to 4. The odds against Macy passing her driving test on the first try are, well, odds in favor are the opposite of odds against. So if 7 is 4, and sorry, if that didn't sound right. If 7 is in favor, that's what I meant by 4, and 4 is against, when I want to go against, what I want is the 4 part first. Okay, it's always what you want versus what you don't want. So when we say odds against here, what we want essentially is Macy failing. Okay, so that'd be 4 to 7 instead of 7 to 4. Okay, so it's always it's 4 and against, but 4 is what you want. Okay, so as soon as we start talking about the odds against something, the against is now what you want. So always think about it as what I want versus what I don't want. Okay. Okay, a committee of 4 people is to be randomly selected from a group of 9 people, including Peter. The probability that Peter is selected to be on the 4-person committee. Well, in order to select Peter, you have to get him, okay? This becomes a combinatorics question embedded in probability, okay? There's 1 Peter in the pile, so I need to take Peter. There's one way to do that. But now I need to get 3 other people, and there's 8 people to select from. So that would be 8 choose 3. Okay, so remember, probability is favorable over total. So right now I've just dealt with the favorable. Okay, there's 1 way to get Peter. So that 1 represents Peter. And then the 8 choose 3 represents everybody else. How do I have 8 people in the pool. I need to get 3 more people so that I have a 4-person committee. Now, the total goes on the bottom. Well, the total, I don't care about whether Peter's there or not there or whatever. So I have 9 people and I'm making a committee of 4. So the total amount of ways to do that is 9 choose 4. Okay. After that, I can just type it in my calculator and I get 4 over 9. okay? Okay, 9 boys and 12 girls have signed up for a trip. Only 6 students will be selected to go on the trip. The probability that only boys will be on the trip can be best represented by the following expression. Now, there's a couple things we need to talk about here. First of all, this question is directly testing your ability to know whether there's permutations involved here or combinations involved here, okay? This is a marriage of probability and combinatorics, which we talked about in the last video. And your diploma will do this, okay? This is part of the curriculum, is to put these two things together. Now, the reason I say they're directly testing you is because I want you to notice these two guys here, okay? One of them says 9p6 over 21p6, and the other says 9c6 over 21c6. Now, remember that probability is favorable outcomes over total outcomes. So in this example, my favorable outcomes is just getting the boys, and my total outcomes is all the kids just taking 6 from all the kids, okay? So what you need to see here is, well, I guess you can't see until you actually did it, but if you put both of these in your calculator, they will actually render the same answer, okay? So that's why I'm saying this question directly tests, do you know whether this is a permutation or a combination? Now, do you? That's the next question. It is a combination because I am, putting these people on the bus to take them to camp. The way I select them to go to camp doesn't matter. Whether Timmy's at camp and Jimmy's at camp, that's no different than Jimmy being at camp and Timmy being at camp, okay? So changing the order does not produce a different result. So it is a combination. To get just boys, I have 9 boys to choose from. And so I want to choose 6 of them, and then that would be my favorable. The total would be, I just have 21 random kids, right? I got 9 boys and 12 girls, so 21 kids altogether, and I want to choose 6 of them. Okay, so the answer would be B in this case, okay? All right, determine the probability that there will be equal numbers of boys and girls on the trip. Well, there's 6 kids going, so if I want equal numbers, I'd need 3. So I need to get 3 boys and 3 girls. So that would be 9 choose 3 and 12 choose 3. That would get me 3 boys and 3 girls. But what you have to remember about that is that we're thinking about this as probability, not just a combinatorics question. Probability is favorable over total. What I just described to you was the favorable portion, okay? Getting groups of equal amounts of boys and girls. So 9 choose 3 times 12 choose 3 would get me the favorable outcomes. What are the total outcomes? Well, it's the same as the total outcomes in the last example. I have 21 random kids altogether, and I need 6 of them to go on the trip, okay? So I end up with 9 choose 3 times 12 choose 3, and then that's going to be over 21 choose 6. Plug that into your calculator, and you will get 34.06%, okay? Okay, so question 11. The mutually exclusive events are described in experiments. So let's just go through each experiment and decide whether there's an overlapping region or not an overlapping region. Okay, if there is an overlapping region, they are mutually, if there is an overlapping region, they are not mutually exclusive. And if there is not an overlapping region, they are mutually exclusive. You see why that statement is confusing? Because the not is in 2 different places, right? If there's not an overlapping region, they are mutually exclusive. You really got to say that a couple times and get it into your head. Okay, so experiment 1 involves rolling a fair die. Event X is rolling a 2, and event Y is rolling a 6. Can I take one die and roll a 2 and a 6 at the same time? And the answer to that is no. So they are mutually exclusive. Okay, they cannot happen at the same time. Therefore, there's no overlapping region there. Event 2, or experiment 2, involves randomly selecting one number from 1 to 10. Event X is selecting an odd number. Event Y is selecting a number that is prime. Can I select an odd and prime number at the same time? Yes, a perfect example of that is 3 or 7. Okay, so there is an overlapping region there, which means those are not mutually exclusive. Okay, by the way, just while I'm talking about prime numbers, 1. Kids get confused with 1 all the time. 1 is not prime, okay? The definition of a prime number is that it has 2 factors, 1 in itself. So 2, 3, 5, 7, those are all prime. The number 1 is not a prime number, okay? Okay, number 3, experiment 3 involves randomly choosing 1 marble from a bag. Event X is choosing a red marble, event Y is choosing a green marble. Can I choose a red and green marble at the same time if I'm choosing 1 marble? No, okay? So that there is no overlapping region there, so they are mutually exclusive, okay? So 1 and 3 only are mutually exclusive there, 1 and 3. Okay, good job. A survey of students was used to estimate the percentage of students who do homework in the evenings and the percentages who watch television. The survey found that 52% did homework, 45% did homework and watch television, a bad combination, by the way. 75% did homework or watch television. Okay, so I know that I have to create a Venn diagram. I know the overlapping region. 45% did homework and watched television. So that's the overlapping region. 52% did homework. Now you got to remember with that guy though, I've already taken care of 45% of that 52%. Do you know what I mean? Okay, and then I know that all 3 numbers in that Venn diagram would add up to be the OR portion, so I can figure out, because they all have to add up to 75. Okay, so if I start a Venn diagram, I put my overlap in first, that's where that 45 came from. Then the 7 comes from the fact that this circle, which was homework, had to add up to 52. So I just took 52 minus 45 to figure out how many only did homework, okay? Now, I know that 75% did homework or watch television. These 3 items represent doing homework or watching television. So those 3 items have to add up to 75. So I'm just gonna go 75 minus 7 minus 45. And I'll get 0.23 as a decimal, or 23%, okay? All right, let me just take that ink off for you. A student is asked to consider 4 scenarios and identify the type of events in each, using a keyed response of 1 for mutually exclusive and 2 for non-mutually exclusive. Describe the scenarios above. So similar question to what I just asked. Scenario A, drawing a 7 or drawing a heart from a standard deck of 52 cards. Can I draw a 7 and a heart at the same time? Yes, I can, because there is a 7 of hearts, right? So there's an overlap there, so that is not mutually exclusive, okay? Scenario B, in a class of 30 students, 16 take French and 21 take Spanish. Okay, so 30 students, what's 16 plus 21? What I need you to see there, 16 plus 21 is more than 30. Think back to set theory, okay? If it's more than 30, that means there's an overlap there. There are students taking both French and Spanish at the same time. So they are not mutually exclusive because there is an overlap, okay? Rolling a sum of 8 or a sum of 11 with a pair of 6-sided dice numbered 1 to 6. Can I get a sum of 8 and a sum of 11 at the same time? No, I cannot do that. So they are mutually exclusive. They have nothing to do with each other, okay? Walking to school or taking the bus to school. Can I walk and take the bus at the same time? No, okay? So they are also mutually exclusive. So I end up with 2 is non-mutually exclusive and 1 was mutually exclusive. So I end up with 2, 2, 1, 1. Okay, good job. I'm hoping that makes a little bit more sense as we spell that out. Okay, independent events. Now this is this little property that you have to understand, and you can take this property right from your formula sheet. If events are independent, the probability of A times the probability of B will equal the probability of the intersection, okay? Take a look at your formula sheet, and it actually physically says that. It says P of A times P of B equals P of A intersect with B, okay? So all we're gonna do here is we're gonna say, hey, does 0.22 times 0.39 equal 0.072. Well, 0.22 times 0.39 equals 0.0858. So no, so it's not A. Do you know what I mean? So we just keep going down the list until we find the one that works. And what you should find is that D worked for you, okay? 0.9 times 0.23 does give me 0.207. So it's those events that are independent, okay? Okay, a box containing 6 green balls and 4 red balls. 2 balls are drawn from the box, one after the other, without replacement. Okay, the actions described will result in events that are dependent, independent, complementary, or mutually exclusive. Without replacement speaks of whether they're dependent or independent, and if I don't replace, then they're dependent. So the answer is A. Okay. All right, there are 10 black, 12 red, 14 yellow, 9 green, 8 orange, and 11 purple candies in a particular package of candy. Sounds like you're going to taste the rainbow to me. If one candy is randomly selected, then the probability to the nearest hundredth that it is a red candy or a black candy. Okay, so remember that probability is favorable over total, okay? So I'm gonna start my fraction here, and let's figure out the total first. We're just gonna add all those numbers together. I've got 10 plus 12 plus 14 plus 9 plus 8 plus 11. I've got 64 candies altogether, so 64 goes on the bottom. That's my total. On the top goes my favorable. Well, what's my favorable? A red candy or a black candy. So there are 10 black candies and 12 red candies. So I'll have 22 favorable outcomes on the top, okay? So now 22 divided by 64 will get me my probability, okay? And that would be 0.34, okay? Okay, a candy dish contains 2 blue candies, 1 red candy, 3 white candies, and 2 green candies. 2 candies will be randomly selected from the dish, one after the other without replacement. The probability of selecting a blue candy and then a candy that is not blue. Okay, so again, I've got 2 different things happening. I'm not replacing, so these are dependent events, okay? I'm gonna end up multiplying the dependent events together. Let's talk about the first guy. The first guy is getting a blue candy. So how many blue candies do I have? I have 2. How many candies do I have in total? Well, I've got 2 plus 1 plus 3 plus 2. That's going to give me 8. So 2 over 8. Okay. Now, the probability of selecting then a candy that's not blue. Okay. Well, we have to think about this. How many candies do we have for the second round? We only have 7 for the second round because I've already taken a candy out and I didn't put it back in. Now, it's a not blue candy. How many not blue candies do I have? Well, I should have 6 not blue candies at the moment, right? Because I took out, the first one I took out assumes that I took out a blue. Okay, so I still have 1 and 3 and 2 that are not blue. So that's where I'm getting the 6. Okay, so multiply that together, I get 12 over 56. And then I just have to reduce that. Okay, 12 over 56 reduces to 3 over 14. Okay. All right, so that concludes probability for us. Hopefully this is feeling really good. And now you have some time to work on the extra practice section. And I will see you for gaming next. Okay. All right, take care, guys.